Today we're going to talk about exact differential equations. Let's go over one example and try to see if we can solve this differential equation by methods that we learned so far, like separable and linear first order ODE. Example. Question says, solve the following ODE. What do we have here? We have e to 2y minus y times cosine of xy dx plus 2x e to 2y minus x cosine xy times cosine xy. And what else do we have? Plus 2y dy. On the right-hand side, we have a 0. Well, so is it separable? Remember that in our steps, step 1, check the classification. Is it separable? Is it linear? And step 2, apply the method. Okay, so is it separable? Can we separate x and y inside the cosine? It seems like we don't have a separable differential equation. Is it linear? Remember the definition of a linear ODE. If I divide everything by dx, the function or the quantity next to y must be in terms of x. But as you can see here, you have x e to 2y, and here you have cosine of xy. So it seems like we cannot separate these and write it in the form of a linear differential equation. So what is this? How can we solve this? We're going to introduce exact differential equations and learn how to solve a differential equation of this form. Definition. Definition of an exact ODE. So, a differential equation of the form m of x and y dx plus n of x and y dy equal to 0. In this case here you have scalar functions functions in terms of x and y, and these are not vector functions, these are just scalar functions. A differential equation of this form is called exact if you have the following conditions. First of all, the partial derivatives of m and n must be continuous on a rectangular region like R. If the partial derivatives of m and n are continuous on a rectangular region like R. And also, the partial derivative of m with respect to y equals to partial derivative of n with respect to x. So remember that we had this case in multivariable calculus class when we dealt with potential functions. So let us check to see if it satisfies the exact differential equation. So here you have your m, scalar function m, and here you have a scalar function n of x and y. So obviously partial derivatives, they are all continuous. Now let us check the left-hand side, partial derivative of m with respect to y. So here you have the partial derivative of e to 2y minus y times cosine xy with respect to y. Okay. So the partial derivative of e to 2y using the chain rule it's just 2 e to 2y minus. Now to take the partial derivative of y cosine xy, first of all, note that your x is going to act as a constant. And here, since you have the product multiplication, you have to apply product rule. So product rule. So you're going to have the product rule for this y cosine xy. The derivative with respect to y is going to be just 1. So let's put it in parentheses. You get cosine xy. Here you have plus y times cosine of x, y, and partial derivative with respect to y. X acts like a constant, so you get xy, sine of xy. Don't forget to change the sign in the middle. So simplify this, we get 2 e to 2y minus cosine xy plus xy sine of xy. This is our left-hand side. What about the right-hand side? For the right-hand side, you have the partial derivative of n, which is 2x e to 2y minus x cosine xy plus 2y with respect to x. Okay, to take the partial derivative with respect to x, y acts like a constant. So we get 2 e to 2y back. 2 e to 2y, and here you have the product rule between these two. So let us apply product rule. Okay, so here you get the minus sign, parenthesis. The derivative with respect to x is just 1. We get cosine xy plus x times y sine of xy, and don't forget to change the sign here. Close the parenthesis. And then the derivative of 2y with respect to x is just 0. Let us simplify. We get 2 e to 2y minus cosine xy plus xy sine of xy, and this is just 0. Let us stop comparing these. 2 e to 2y, they are the same. Then negative cosine xy, which is equal to negative cosine xy. And as you can see, the final terms are equal as well. So what's the meaning of that? It means that this differential equation is exact. We have an exact ODE. So question is, how do I solve this? So is it exact? Yes. So how do we solve this? To solve an exact ODE, let's write this down here. First of all, we are looking for a function in x and y such that f of x and y is equal to the integral of m dx. And here, after finding this integral, it gives you a function that has eventually, when you're taking the integral, the constant of integration, which is equal to g of y, or a function in y. And in step 2, we're going to take the derivative of f with respect to y and set it equals to n of x and y to find g of y. And finally, the last step, we're going to have f of x and y equals to a constant like c. So that's how we get the solution of this differential equation. Remember that you can change this and write it with small letter like f, or you can keep it as capital letter. It doesn't matter if you open any differential equation book, you might see different letters that they're using representing their solutions. So it's not separable, it's not linear, but we found it is exact. Again, remember that this is exactly what we did in multivariable calculus class. So let us follow step 1. The solution set for this differential equation is equal to, how to find the solution. Okay, here you have your solution equals to f of x and y equals to the integral of m e to 2y minus y cosine xy dx. So the integral of e to 2y with respect to x is not very hard to find. It is equal to x e to 2y. Here minus the integral of y cosine xy dx. Remember that here you can use substitution. If u is equal to xy, du is y dx. We have all the missing information and we can write f of x and y equals to x e to 2y minus sine of xy plus constant of integration, which is a function in y. If we take the derivative with respect to x, the derivative of gy is going to be 0 because it's just a function of y. We are not allowed to just assume it is just a number or a constant. They have to think about this as a function in y. Now, in step 2, take the partial derivative of this solution that we found some part of it and set it equals to n. So the partial derivative of f with respect to y is equal to, here you get 2x e to 2y. Here we use the chain rule minus x cosine xy and plus g prime of y. And now we set it equals to n. But what is n? Let me just put this in a box so we don't get this confused. So it's equal to n. What is n? N is 2x. 2x e to 2y and like this. 2y minus x cosine xy plus 2y. Very well. So check this. 2x e to 2y, 2x e to 2y, you're setting these two equal to each other, minus x cosine xy, minus x cosine xy. So what's the meaning of that? It means that your g prime of y is 2y. What's the meaning of that? It means that g of y is equal to y squared plus a constant of integration. So we found another missing piece of the solution. So in step 3, the solution f of x and y equals to x e to 2y minus sine xy plus y squared plus c. So we found the solution for this differential equation.